So jumping into our notes for our Unit 3 and alkyne chemistry, alkynes are going to be hydrocarbons, meaning we're going to have carbons and hydrogens that have two carbons which are triple bonded. And we're going to go through and we're going to talk a lot about their synthesis and then reactions with them. And we'll see that they share a lot of similarities with alkenes. Alkenes being the double bond alternative. So one of the first things we want to talk about is how do we make them? So one of the most common ways to make them is actually through a very easy elimination reaction, typically like an E2. If you have a leaving group, like let's say a bromine, and then one away, there is a hydrogen, you can get an E2 reaction where you'll have a strong base. That base will abstract a proton, form that double bond, and kick out your leaving group in a concerted reaction. E2s are going to be better than E1s often because you're not competing with like the SN1 or SN2. E1s and SN1s compete a lot where E2 and SN2s compete a lot less. Now, because of the fact that we're going to be forming a triple bond, we are going to have two kind of like back-to-back E2s that occur. And there are two possible like scenarios where we put our leaving group. And here our leaving group I've just generically put in as X. So we can imagine a scenario where between two carbons, we have a bromine on each of them. This is going to be known as a vicinal dihalide. The other possibility is having both of your bromines or whatever your leaving groups being on the same, and these are known as geminal dihalides. Now, the difference between these will actually impact kind of like where double bonds form depending on the choice of the base. If you wanted to kind of think about general ways to kind of like remember the difference between a vicinal and a geminal dihalide, I have a little bit of kind of like nomenclature hints here. The geminal actually comes from the Latin word Gemini, which comes from the idea of twins in whatever it's called. I'm sorry. I'm not an astrology person, but the astrology stuff. So you can have them on the same, which are like twins, which is Gemini, or you can have them on opposites. And if they're opposites, they're nearby, but not at the exact same location. So you can think of like you and your neighbor, both on the same street, but not in the same house. So you're in the same vicinity. So those are the kind of like two different types of starting materials we might have. A vicinal dihalide where you have bromines on separate carbons, or a geminal where they're on the exact same. Now, each of these will have the ability to undergo E2 reactions. So to kind of give just like a quick preview, we'll look at an example here. So here we have a generic starting material, and we have two bromines, both which have wedges. Now, the stereochemistry being the same between those bromines will kind of be things that we'll consider, because we do know with an E2 reaction, we do need anti-periplanar. So if I think about where my hydrogens are, which are ones that are not drawn, they're going to be dashes. If my bromine was one had a wedge, the other had a dash, then your the hydrogen that's going to be one away wouldn't actually be anti-periplanar. And that's going to be one of our kind of core requirements for our E2, so you would not be able to actually get that to occur. So considering anti-periplanar is going to be something that's really important. But in general, we can use a base here, or we'll just use a hydroxide. That hydroxide can abstract a proton from our starting material. That's going to, instead of doing a lone pair specifically on like a conjugate base, if we just do like acid-base stuff, instead that's going to push it into the bond because we have a good leaving group one away, which can leave. That would then give us a double bond in between where our two bromines are, while still keeping our first bromine. That's our kind of very first E2 reaction that we're able to do. Now, the stereochemistry doesn't matter nearly as much because these will always be on the kind of like opposite sides, if we kind of think of almost like E and Z in terms of double bonds. The excess, if you had excess base, you can then do this again. So I'll then have more hydroxide come, abstract another proton, make a triple bond, and then your bromine leaves. Now, if we want to think of our product, overall my backbone, I have 1, 2, 3, 4, 5 carbons. Drawing alkynes does take a little bit of kind of like practice because of the fact that your triple bond needs linear geometry, so you can't show that same zigzag. So you'll have to have this kind of like extended like straight segment. So if I want to think of my carbons, 1, 2, 3, 4, 5 in terms of my main backbone, and then I have 2 more at my, I guess the 4th position if we were going like proper. So our product would look like this with a triple bond between our 2 carbons. That's our kind of like stereotypical like E2 reaction, kind of just taking what we've already learned from Orgo 1 and then just kind of putting 2 bromines and just having a small extension of that. So 2 back-to-back E2s are able to give us a triple bond. Now, depending on if we have a vicinal or geminal dihalide, the choice of base might matter a lot in terms of what type of product that we make. And there is going to be 2 main types of bases that we're going to talk about. And this next segment has kind of a big paragraph that's going to kind of walk through that. So in general, the first step of this reaction, which is going to be our first E2, happens decently fast. The second step is normally a little bit harder. So often you'll need some kind of harsh conditions, and that's going to mean a pretty strong base. And there's going to be 2 different types of conditions which we're generally going to be thinking about. The very first one, if we kind of think about our arrow, is going to be KOH, and we will often have really, really high temperatures. Often you'll actually do this with molten KOH. So if you take KOH, heat it all the way up to 200 degrees C, it will turn into a liquid. And then you use that mother liquid to go through and do your reaction. 200 degrees is quite toasty for a reaction, so that is a very, very harsh condition. The other typical example you might see is going to be your NaNH2. This is your sodium amide. Both of these are really, really strong basic conditions that are able to do a E2 type reaction. However, there is one important difference between these in terms of where they're going to make your triple bond, especially if you have a geminal dihalide, and that's going to be when they're on the same. And your kind of main important difference is in your case of your KOH, you're going to prefer internal, where your sodium amide is going to prefer terminal or outside. We'll walk through an example in a second to kind of show examples of both of these and kind of like why it occurs. But that is kind of one important difference. So KOH inside, NaNH2 outside. So let's walk through a few kind of quick practice problems with regards to this type of reaction. So in our very first one, we're going to use a vicinal dihalide. So we have 2 bromines, and we're using KOH at 200 degrees C. Now, when we're thinking about making a triple bond, if you ever have a case where you have vicinal, meaning I have my leaving groups on different carbons, these are super easy and we don't have to think. It doesn't matter if we use KOH or our sodium amide. The triple bond always must be in between our 2 different groups. So when we're drawing our product, we'll draw in here. I'm going to draw this real quick. So a product like here, so in terms of our carbons, this carbon would be our blue one, and then 2 and 3 would be where those are, and then you have your branched, and then your 2 methyls. Anytime you see a vicinal dihalide, that is one that's nice and easy. Now, if instead you have a geminal, so in our next example, we'll have something that's kind of similar. We lose a methyl, looks like, but we have a geminal, or both of our bromines are on, or leaving groups, well, most of the time bromine, but could be any leaving group, are on the same type of carbon, Now there's two different choices. We can either put a triple bond over on this left side or over on this right side. And that's going to be the difference between our internal and our external for the in or out. And the choice of base here is going to matter a lot. So here in this specific example, we're using our sodium amide. And sodium amide is really good at doing external, and it will not do internal. So here, your product would be a structure that looks like this. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, with your triple bond all the way at the end. Now, if you change this just a little bit and instead used your KOH under really hot conditions, you'd actually get a different product, which would look like this, 1, 2, 3, 4, 5, yep. And that being an internal alkyne or triple bond rather than your external or your terminal. That is one kind of really important nuance that you need to think about when you have your geminal dihalides or both of your leaving groups on the same. Now, if we consider our next example here, where we have a vicinal dichloride, here we are using our NaNH2, which likes to go on the outside. However, it doesn't have a choice because we have to do our eliminations directly between. So this is actually going to still give the exact same product as we had in the very first one, where we have that triple bond in between our two different chlorines. So if there's no choice, it has to go in between. But if there is a choice, and the chances where the cases where there will be a choice are going to be with our geminals, then the choice of your base is going to matter a lot. Now, one of the reasons why you actually get your terminal or your outside form is actually going to be because your NaNH2 is really good at deprotonating your alkyne. That is going to be removing your H at the end, and that's going to be super helpful for reactions. And we're actually going to give an example of that in just a second, where we're able to do, like, for example, an SN2 reaction with a triple bond. But our kind of key things here are, in general, one of the ways we can make a triple bond, which is going to be our alkyne, is going to be through an E2 reaction. That E2 reaction can happen on a variety of different types of structures. We'll need two different leaving groups, most of the time being halogens. If they are on the same carbon, we call them geminal. If they're on the opposite, we call them vicinal. And depending on the type, vicinal will always put in between, your triple bond in between, where geminal will depend on your choice of base. KOH under molten conditions will go on the inside, where NaNH2 will go on the outside or at the terminal. And those are kind of our like simplest and most common ways to make alkynes. We'll go ahead and stop there, and in our next video, we'll start thinking about different types of reactions we can do with alkynes as our nucleophile.